Hello, my name is Hallie, and welcome to this exploration of entropy. Entropy is a key component of thermodynamics, and having a better ability to define this state function as well as predict how the entropy of a system will change when stress is applied to that system will certainly be an advantage on test day. And by completing this review, you'll have a better ability to define and compare the entropy of two systems, such as the ones presented here. This system on the left is very organized. Everything has its place, so it would be a lower entropy system, while the one on the right is very disorganized. There's lots of options of where we could put stuff, and so it's a higher entropy system. And you might be wondering, why are we comparing the entropy of these two systems and identifying them as being either low or high with these words in quotation marks? And well, that's because entropy is a little bit more complex than just being a measure of disorder. But I don't want to ruin the surprise just yet. By the end of this review, you'll have a better ability to attack questions, such as the one at the bottom of the screen, which asks you to predict how the entropy of a system will change during a chemical reaction. Entropy is defined by the second law of thermodynamics, which states that energy will spontaneously diffuse from a localized area into a more dispersed or spread out form. And we see examples of this in everyday life. But we are able to prevent the movement of this energy by adding work to a closed system. For example, if you think of the smelliest room in your house, you know that that odor will diffuse throughout your building all day long. However, if we apply a little bit of work, such as shutting the door, we can protect the rest of our house and prevent that entropy or that random diffusion of the odor throughout our building. Entropy is the numerical value that we use to measure the spontaneous dispersal of energy at a specific temperature. And entropy is always represented by the letter S. And it's presented in joules per mole Kelvin. And if you remember from your physics studies, any time that we're working with energy, we expect to see that our units will be in joules. Entropy is a ratio of the heat gained or lost by a system over the temperature of that system in kelvins. Notice that both entropy and temperature are measured in kelvins, so be sure to convert on test day. Since entropy is a ratio of heat to temperature, we would expect that as the heat energy of a system increases, so would the entropy of that system. And as the heat energy leaves the system, the entropy would decrease. Let's think about boiling water for just a moment. Liquid water has a certain amount of entropy because it is able to disperse over an area. However, when we add heat energy to that system, we create steam. And we know that steam will disperse all over the place, and it's very hard to contain. So we know that steam has greater entropy than water, partially because of its ability to disperse, but also because it has a greater amount of heat energy. Now that we know how to define and calculate entropy, there are two other concepts and formulas that we will want to be familiar with for test day. The first being that the second law of thermodynamics states that the entropy of the universe will always be increasing. Let's think about a specific example, such as a refrigerator trying to cool the air inside of it. The refrigerator will apply work to the air inside of the cavity in order to remove heat from the system and therefore decrease the entropy of that system. However, in order to remove heat energy from the interior of the refrigerator, the motor of the refrigerator had to do work. And as that motor did work, it released heat into the surroundings. And the heat energy released by the motor is much greater than the heat energy that was removed from the cavity of the refrigerator. So even though we were able to decrease the entropy of the interior of the refrigerator, the motor continued to do work and released entropy into the surroundings, and therefore made the room hotter. So the entropy of the universe did increase. The second formula is how to calculate the standard entropy of a reaction. Standard entropy is another state function, so it's pathway independent, and all that is important is the difference between the final and initial state. So we would simply take the entropy of the products and subtract out the entropy of the reactants. For example, on test day, you could be given a system like the combustion of a hydrocarbon in the presence of oxygen, and then given the entropy of each compound, and then asked to calculate the change in entropy for the entire system. Let's now try our practice question from the beginning of this review, which asks us to predict which of the following molecules will have the greatest entropy following a combustion reaction. And the correct answer is D. We know that entropy will have either a great heat content or it will have the greatest ability to disperse its energy. And we know that combustion is simply burning a hydrocarbon in the presence of oxygen to create water and carbon dioxide. Since we don't know a lot about the heat content of this reaction, we'll have to go off of the ability of each of these molecules to disperse themselves over a larger area. An N-pentane having 5 carbon molecules will be able to create 5 carbon dioxide molecules and therefore have the greatest amount of entropy because all the other molecules will not be able to create 5 carbon dioxides. Let's highlight the key points that we will want to remember for test day. The second law of thermodynamics states that energy will spontaneously move from a localized area to a more diffuse one, and entropy is the numerical value that we use to measure the movement of energy. And remember that the entropy of your universe is always increasing. Well, folks, that's entropy as it applies to the general chemistry portion of your exam. I hope that you now have a better understanding that entropy isn't just a measure of disorder, but how energy is able to diffuse throughout space. And I encourage you to think about the entropy of the systems that you encounter in everyday life, such as the boiling water in the refrigerator. Thank you for joining me, and best of luck preparing for the MCAT.